We all heard the phrase messy data or bad data, right? But it's a little unclear what that means. I mean, it might be just that a measurement is bad, like there's actually a noise or something's gone wrong. But in fact, for data scientists, it's often more subtle and more insidious. So there's a number of ways in which data can be confusing or misleading or messy that aren't necessarily just meaning that it's wrong, just that it's confusing. So a lot of this is adapted from this bad data guide that I highly recommend you check out. It's super cool. So first a brief bit about data types. So different languages and things will have different types of data, but really common ones are integers, right? So those are just whole numbers. You also got floating point numbers. So for now, you can just think of that as decimals. And then strings, so that's just series of characters, and booleans, like a true or a false. There's a bunch of other types, but it seems like even within just this type, because we're sort of constraining it so much, like how could it be messy, right? This seems really well defined. Well, there's a ton of things that can go wrong. So a really common one is missing values. So missing values are bad enough when they're just missing, but worse, they can be missing in like a number of subtle ways. So null is commonly used placeholder. There are other ones though. So nan stands for not a number, and it's a placeholder for when you do something in math that you shouldn't have, and you end up with a number that's not really a number. So an example would be dividing by 0 or something. Worse, a lot of folks will go through and fill the missing values so that they're not missing. So that can be good if you do it in like a principled, thoughtful way. But often they'll just fill with a 0 or fill everything with a -1, right? So the census data, the U.S. Census data does that a lot, where they just put a -1 in anywhere where there's stuff that isn't there at all. So like the number of people will be -1 instead of just missing. Sometimes there's just an empty string. So there's a string with 0 length, which is just two quotes next to each other. There's also some specific ones you got to watch out for. So dates and locations. So 1900 and 1970, especially like January 1st at midnight, are really common filler values because there's multiple ways of keeping track of time in computers, but it just happens to commonly start at those locations. And so what'll happen is they'll put in basically a 0, and then the earliest time that it records is that time, and so it just goes with that. There's also this picture of a buoy, which is sometimes called Null Island, and it's right at latitude and longitude 0. And what happened with it is the Strava fitness tracking app, which uses it like tracks your run or bike path or whatever, says it is one of the most common places to go for a run. And the reason is some phones, when you turn off tracking or whatever, will just send empty values, and that's interpreted as a 00. So it shows up as an artifact in their data. So a related concept to missing values, those are all values that are missing where there's like a row of data and there's a value that's not there. Another thing that can be missing is whole sets of data, swaths of stuff that you expect to be there. So if you're looking at U.S. national data, you might expect there to be 50 states listed. In fact, there's usually more than 50 because DC gets split out and things like Puerto Rico and American Samoa are often included. But if you looked at a bunch of data and it said this is national data and then it only listed like 35 states, you'd be like, hey, something's gone wrong. Something's missing, right? Okay, so for the rest of this messy data talk, we're going to pretend that everything is not missing. So we have a complete picture and an accurate picture, meaning there's not the data that's there is not wrong, and it's still going to be messy. So dates and units are a huge problem. Time zones are actually just a nightmare for computers, and programmers have spent it's sort of a meme at this point, how much time programmers have spent figuring out time zone stuff. But one that especially folks from the US are not aware of is that dates are written very differently in different parts of the world. So there's 2 dates listed here, and depending on where you are from, you might guess one of them is in September or the other one. And in fact, without additional knowledge, I think you really can't say for sure. So if you know where the data originated, or if you know how it's written, that's helpful. But this is actually deeply ambiguous. You don't know which of those is in September. A similar idea is with units. So if something weighs 87, you really don't know what that means, right? It could be 87 grams, and it could be 87 pounds, right? You just don't know. And then another really common one is misspellings. So it's a little bit different as places, but and it happens all the time with different things. But there's this real question of disambiguating and whether or not you can group things that are similar. So if you see a spelling, a city in California spelled Los Angeles, is it the same thing as Los Angeles? Well, this is the kind of thing that the data scientists have to make choices about. Okay. Let's say we sort of unambiguously understand the units and the format of everything and all the rest, and there's none of the noise or whatever. What else could be wrong? Okay, numbers aren't always quite numbers. So here we're looking at some integers. This top one looks like it's an integer, about 1.5 billion, but it's probably a date. There's a thing called a Unix timestamp, which is super common in computing. And what the Unix timestamp does is it looks at the number of seconds since January 1st, 1970 in the GMT time zone. Okay, so I think we just passed 1.6 billion, but it's actually a date. And so it should properly be interpreted as a date and not really as a number. The next one looks like a number, but because the units are included and it's got some commas, it's going to show up like a string. And this is really common in data where there's some additional formatting, and so when you load it into the code, into the computer, you have to pull the number out and turn it into an integer because it's got stuff around it, right? And then the last one certainly looks like an integer, but it turns out that leading 0 is important. So this is a zip code for sending mail and whatever in Boston, Massachusetts. And a bunch of them have these leading zeros. And the problem is if you store that as an integer in most code, it will trim that leading 0 out. But that 0 is actually super important to the meaning of it. Zip codes are always 5 digits. So it's really not an integer in the way you think of it. It's a zip code, which is a special idea. Cool. Strings have their own problems. One of the common ones is encoding. This is less common now. The standards are getting a little better, but it used to be really common when you visited a website to see question marks all over the place. There are different ways of encoding characters into strings, and when you get it wrong, it's really terrible. This is a problem I have about twice a year with Python. Now that Python 3 is much better at it than Python 2 was. ASCII, ASCII, and Unicode are the most common, but there are other character encodings. So sometimes you'll see things that are messed up. And so the best thing to do is to figure out the source of the problem, and then to also spend a lot of time looking at your data. But really, this is just a machine translation problem where if you load something and you say it's encoded in this standard, but it's a different standard but just slightly, then you'll just see occasional errors in the text, which can be really subtle. Really common with the curvy quotes and curvy apostrophes, stuff like that. Okay, so even if we have a really crisp view of our data, it still could have all sorts of other problems that make it unsuitable for answering our questions. So one example is it could be too coarse. And by too coarse, I mean that you could want more resolution that is available. It also could be too granular, right? Then you can possibly roll things up to be at another definition. But this is the kind of work that we have to do to manipulate stuff to get the answer we want, right? So when the data is too coarse, there's not much you can do. You can try to interpolate and guess, but it's really a guess. But when it's too granular, there is work to do. Probably the biggest source of bad data or messy data is collecting data that doesn't actually measure what you think you're measuring, right? So an example here is we could be looking at some activity data. So physical activity, think like a Fitbit or an Apple Watch or something, and we have a year's worth of data from 10 million people, and we've got this activity tracker, and we do all this stuff, right? And we want to extrapolate from that to all the citizens in the U.S., right? So certainly there can be some real problems with that. And right off the bat, one thing is the group of people that use activity trackers are really different, right? So because you're not picking a random sample and designing a study carefully, it's not going to generalize in the way you want. So there's a couple of ways to fix that. You can try to tease out some stuff, but the better thing is a random sample. So you could do that. You could randomly pick 1,000 people, and you pick folks of all different ages and whatever. And so we're going to pick in San Diego County, so it's easier to interview and follow up with them. And because this is a hard thing to do, we're just going to do this study for 3 months, right? So on one hand, the randomized study is great because now we're seeing a much more representative swath of the population. But unfortunately, the population is people who live in San Diego, right? Which is a different population than the rest of the country. And maybe worse, it's summertime. And summertime is going to have really different activity than other seasons. So it could be a real challenge. So yeah, non-random samples, seasonal variation, and this last one we'll do some reading about later, but it's really about this idea that there can be, if you just collect data until you sort of see the results you want, that gives you misleading results. So that's also going to be a problem. Okay, so one final one I'll leave you with from this is this idea that there's a bunch of other data types. So when you're loading data to use it as a data scientist, it often comes in all sorts of weird containers. So in Data Science 10 or in other intro-level data science classes, you're often going to see columnar data, right, which is like a CSV or a table. It's flat, it's got defined types and all the rest, maybe some escaping. It turns out CSV doesn't have a strict standard, so there's some weirdness in there, but generally you can load those up. But data can be locked up in all sorts of other formats. So PDFs are notoriously difficult to rip apart and get data out of, right? The screenshot on the right here has some plots, some numbers, all the rest. In this class, we're going to deal with a bunch of weird stuff around images and sound recordings and words and the internet and just trying to like grab all that data and munge it around to try to make it pretty good. So I'll actually have another session on messy data and what it can look like and the different ways it represents. But that's it for today. So thanks.